to kind of get going on what I'll be talking about today, I'm going to walk you through a training and image segmentation model with PyTorch 1.13.1, where we will be identifying roads and speed limits from satellite images. And we're going to be doing this all on the new 4th gen Intel Xeon Sapphire Rapids CPU. All right, so here on the top of the notebook on the left, I've listed, the Discord and then some ways you can connect with me. And those should all be in that notebook that you can look at on the GitHub there as well. All right, so the first thing I wanted to point out is that I'm working on what's called the Intel Developer Cloud, which you can sign up for in the beta here. I have a link, cloud.intel.com. And if you want free access, please get in touch with me after the talk today, and I can actually get you on the Intel Developer Cloud. I can get you, working with the latest hardware that we have available. I have some nodes that have actually been assigned to me so that I can pass those out to those who are interested. But yeah, that's normally the process you'd go through. I'll just click on this link, cloud.intel.com. And then can you still see my screen with this Intel Developer Cloud?
Yes.
Okay. And then you would go to sign up here. I already have an account, so it'll just say like access denied. You already have an account, but you'd go to sign up here and then kind of follow the steps to get going there. All right. So, and then I just highlighted here, coming soon, I'm hoping to provide a new tutorial because PyTorch 2.0 will be released within the next couple of weeks, I think. So I think it's a pretty big release, and there will be a number of pretty cool changes happening to PyTorch. All right, so moving on to the next section, key references. So, much of my code was actually taken from the Cressy repository, and I'll just click on that link as well and show you the GitHub. It's essentially, Cressy stands for City Scale Road Extraction from Satellite Imagery. And I've kind of walked through this myself to do the training myself. So what I'm saying is I haven't invented a lot of the training code today. It's a lot of it's taken from here, and then I've modified it some for working on the CPU, and then also putting in some additional optimizations with Intel extension for PyTorch. And then here I just point out that I was able to piece together a workflow from using some of the notebook examples here. And then I wanted to point out that there are some great Medium articles for detailed explanations of how to get started with the SpaceNet 5 data. And I did use some of these in kind of constructing my notebook and understanding the data set, going from pre-processing the data to training to post-processing. And then the last Medium article I have here is like the talk about the winning model. For this, there is a competition called SpaceNet 5, and they have these SpaceNet competitions each year with different kinds of satellite imagery. And so that one talks about kind of the winning model for this particular competition. I also referenced 2 Hugging Face blogs by Julian Simon. He ran some of his tests on the latest Sapphire Rapids on AWS. So whereas I'm running it on the Intel Developer Cloud, they are available in preview on AWS as well. And then an introduction to the hardware for today. So I'm going to be working on the 4th gen Intel Xeon CPU, codenamed Sapphire Rapids. It was just released in January, so I'm excited to be working on it and showing it. It's all new to me as well. And so, yeah, the machine that I'm on is bare metal. So it has 2 sockets, like 2, kind of physical CPUs, or 2 nodes, and they each have 56 physical cores. So it's a very big beast machine. And then those are hyper-threaded to 112 vCPUs for a total of 224 virtual cores, and then 504 gigabytes of memory. And then the thing I'm probably most excited about is this new Intel Advanced Matrix Extensions engine. It's a built-in AI acceleration engine, and it supports BF or brain floating point 16 and int8 data types. So that can greatly help with the speed of training and inference. So that's a really exciting new extension. And essentially what it helps with is matrix multiplication, which If you know anything about neural networks, there's a lot of matrix multiplication in different components of your network. So it kind of passes some of these kernels over to this AMX engine and then passes them back. All right, so I'll go briefly over just in general what some of the AI optimizations attempt to accomplish. So one of them is on the operator level, so parallelizing over threads, mixed precision and quantization, data layout optimizations. And then number 2 is at the graph level, so operator fusion, for example, convolution and ReLU. Runtime would be like thread affinity, multi-streams, NUMA control, and memory pooling. And just a couple of examples of things that I used and made sure to install, going into this one of them is OpenMP and the other one is NUMA. And I've outlined here just a few of the, you can see these export commands, a few of the environment variables that you can set. And that's for this OpenMP. And then I also have NUMA CTL installed for controlling local memory access. And the nice thing with this is you can actually specify which cores you want to use, and then you can say, oh, I only want to use it on this socket instead of kind of communicating across both sockets. So in this case, I'm saying, cores 0 through 35. And then memory node ID would be 0 or 1 for the socket. And I found that I wanted to stay on one of the sockets because when it had to communicate across sockets, it slowed down the training. Now, when you end up getting on some of these machines, in the future, it may be that you'll be on a virtual machine where you only have access to one socket, so it's not as big of a deal. But in my case, I needed to make sure I was only on one socket for the training. The other thing that I'll point out is that both PyTorch and then the Intel extension to PyTorch, they have helper scripts. So you don't have to explicitly use NUMA-CTL and set these environment variables, but they do need to be installed so they can work in the back end. So I'll go over that when I go over kind of the environment setup. I won't spend too long on the environment setup, by the way. But yeah, so PyTorch for CPU, just briefly introducing that and then Intel extension for PyTorch. So Intel's main goal is to make this default PyTorch simple to use and perform it on CPUs by upstreaming all the optimizations we can into the main branch of PyTorch. It uses the default PyTorch uses OpenMP for multi-threading, and we've also upstreamed something called 1DNN, which provides these optimized deep neural network primitives for Intel CPUs. So that's kind of already all baked into PyTorch. When you do that, you have to get the CPU version of PyTorch, but that's directly from the PyTorch website. Now, Intel extension for PyTorch is just something that provides some additional acceleration that has not yet made it into the stock package. So it's early access to optimized kernels, runtime extensions, and one that's come out that's most relevant, I think, for this talk is the mixed precision with BF16. So I say here at the time of writing, so today it's in this Intel extension for PyTorch, but it should soon be upstreamed into the stock version. The reason it's so significant is because BF16 requires only half the storage of FP32, which is typically what people use. And so that reduces memory bandwidth, computation. So it's a really helpful piece. And the nice thing is that the new hardware, the Sapphire Rapids hardware, also supports this BF16, which on previous Xeon versions wasn't supported. So I put the link to the IPEX GitHub there where you can clone it or pip install it, and then the product page from Intel. And then I found this other Medium article, which I found was helpful. Like if you have more questions about 1DNN and BF16, there's this Medium article called Accelerate PyTorch with IPEX and 1DNN using Intel BF16 technology. So I'm not going to spend the whole talk talking about that, but I just wanted to make you aware that there's that resource available to you. And then 3 tools that I wanted you to be aware of that we will cover in today's workshop regarding IPEX is, one of them is IPEX.optimize. And that kind of bakes in all these optimizations into a single line of code. It's really handy. And then there's another one for auto mix precision, which I've outlined here, and I'll get into those later when I'll actually show you, where to edit the code or what I did to edit the code. And then there's a launcher script, and that's one of those helper scripts I was referring to called PyTorch CPU launcher. It's called IPEX run. That's the code that you run in the command line to run your training code. And you can specify some of those, core count and which socket and those kinds of things in the arguments for this IPEX run. Now, okay, so that's on the hardware. Now, the model architecture for today is ResNet 34 plus UNet. So it's a ResNet 34 encoder and then a UNet decoder. And that was kind of the winning model for this, competition. So I just tried to emulate that. And the operating system that I'm on today is Ubuntu. So, and then the Linux kernel, you can see on the right is 5.15. Yeah, and then I like to use this ls CPU command. I'll run that here in the notebook, and it'll show me, what's on the CPU. So I can see I have 224 virtual cores, like I was talking about. I have 2 threads per core. The physical cores per socket is 56, 2 sockets. So this kind of just tells me a little bit about what processor I'm running on. And the other thing I'll point out, there's a lot of flags here, but the ones I'll point out are these AMX flags. So that's showing me that, hey, there actually is this advanced matrix extensions on the hardware. And so I always check that to make sure, hey, is this actually enabled on, on this CPU? So yeah, I've outlined that on the bottom there under flags. You can see those AMX tags for the BF16, the int8, and the AMX tile. So it's available for use. All right, so this is the environment setup, and I'll kind of run through this pretty quickly. If you want to look at it more carefully, you can just look at the notebook later. But I'll kind of run through it quickly, and there's some important points I want to make just to draw out in the part. So the first is, if you want to register on the Intel Developer Cloud to get going, you can do that. I've already pointed that out. And then the next thing is I've put in here with sudo apt-get installing some packages that go into the backend kind of before you install the typical Python packages. So some of them are to do with this specific Cressy repository that you have to have installed kind of for the backend for that. And so I won't go in detail through all of those, but there's a couple that are key for getting the most out of the hardware. One of them I already mentioned, which is NumaCTL, and the other one is libmalloc. So those two are important for, like, in general hardware, and we'll use those IPEX run or those launcher scripts. And I'll point out here that I do have AWS CLI, which is the command line interface for AWS, because the data sets will actually download from an AWS S3 bucket that's publicly available. Okay, that's enough on apt-get. The next step is setting up an Anaconda environment. Probably a lot of you may have already done this, but I've outlined some of the steps that I took to create the, just using Miniconda environment, and then, creating a virtual environment, which I've called Py39 because I'm using Python 3.9. And yeah, and then activating that and then installing a few Conda packages. The two that I'll point out are Intel OpenMP, which I pointed out, and then gperf-tools, which is like a profiling tool, Google profiling tool. Again, those are helpful when you're running the training to make use of, in the case of Open, the threading and all of the core control, and then kind of profiling with the gperf tools. And then the other ones I would say are, again, largely to do with this Cressy repository that are very specific to this data set. Okay, and then installing pip packages. So this is probably a lot of what people are used to, using pip to install different things. So first one, I'm just upgrading pip, and then the second one, I'm installing a specific version of setup tools, because I found that for this repository, this GDAL version which you have to use requires this version of setup tools. Just one of those things that as you're testing out code, you have to kind of learn these things. And the next one is installing PyTorch for CPU. That's off of the PyTorch website. And then the next one is actually installing all the requirements. So I've listed those requirements down here. And the one that I'll point out, there's a number here, but the one I'll point out is this Intel extension for PyTorch. So it's just simply pip install, Intel extension for PyTorch. And then, after that, this last line actually puts this kernel into the Jupyter notebook. So once I've, made this Py39 kernel, then I can, stick it in here so I can pick that kernel from the Jupyter interface. Okay. Cloning the Cressy repository. So in my case, if you look on the right-hand side, I've already cloned this Cressy repository with a bunch of code in it that I'm going to be using. And then the last step is downloading the data. So like I pointed out, there on an S3 bucket, you can find the data, and you'd have to install that AWS CLI, like I pointed out, and then use this AWS configure command. And then you have to enter your AWS access key and secret access key. But you can freely, create that, and then you have access to run these commands. So I'll run them here in the notebook. And what I'm doing is I'm just listing out the data that you can possibly download, and I've listed kind of the sizes. So they're between 5 and 35 gigabytes, just different components of the data. And the main one that I'm using for today is this Moscow data set. It's like 1,300 images or so. So it's not like a huge data set, but each of the images are 1,300 by 1,300 pixels, which are fairly large for like image training tasks. A lot of times, you'll do like 500 by 500 or 200 by 200, something like that. So they're fairly large in that regard. But that's just listing them. And then I have listed the downloading or like the copy commands that you would need to use for this AWS CLI as well. And then, so they're kind of zipped up, so you have to unzip them. And then, so that's and then if you want to download a whole folder, here's an example of downloading a whole folder from S3. If you wanted to download like all of the data, which might take some more time, but that's so. And there's SN5 and SN3, and they're all like city satellite image data, and both of these SN3 and SN5 were used in this competition. So they had access to kind of training with those two big data sets. Okay, there was one more step I said last, but the last one is just launching Jupyter Labs, and you may be already familiar with that, but I just put the command here for how I launched this. I typically prefer to use something called tmux. So tmux here on my screen, and then it's just a suspended window, and then I can exit out of that before I launch Jupyter, so that it's not just sitting in my main window. And then in order to connect in, you can create an SSH tunnel. So I've already done that. And then I've been able to, as you can see at the top of my screen, localhost 8080. So that's how you would connect into Jupyter. This other command, some of you may know, it's just to show you how much space you have on your disk. And so before you go and download a bunch of data, it's always good to check how much space do I have on my disk. Make sure I have enough. Okay, so for this particular notebook, I'm not actually importing a ton of packages. I'll be running things in the command line and just kind of showcasing what I've done. But I do have a few, mainly just to show some of the data, to kind of showcase, here's what the satellite images look like and some of the masks that we create. So that's, importing those Python packages there. So I'll go ahead and run that. And this next part is kind of on pre-processing, and I don't want to spend too long on this, but I think the time I want to spend on this is mostly just so that you can familiarize yourselves a little bit with the data set. Obviously, once you spend more time with data, you get to know it a lot better. So I know it pretty well because I've spent quite a bit of time with it. But I'll try to introduce it to you. So the images have these kinds of names, this SN5, roads, train, et cetera, et cetera. And the SN5 means SpaceNet 5. The PS RGB means pan-sharpened 3-band RGB image. And if it's a PSMS, it means pan-sharpened 8-band multispectral image. So they actually provide like kind of two different kinds of images for the data set. One of them has 8 channels and the other one has the typical 3 RGB channels. And so when you look at the shapes of those images, like the shapes of the arrays, you see that there are, 1300 by 1300 by 8 for the 8-band multispectral images, whereas the RGB ones are 1300 pixels by 1300 pixels with 3 RGB, channels. So here in the notebook, I'm just going to show the 3-channel RGB images. The 8-band are a little bit harder to visualize, but feel free to explore ways to visualize those 8-band images. And then I'll point out too that each of these images are like a chip or a clip of a larger satellite image. So you can imagine typically on a GPU, you can't load like really large images into memory. So you kind of create smaller batches and smaller images. So they've kind of, chipped these down into smaller images to do that. And then, so basically the goal with there's these satellite images, and the goal is to create these masks that have pixel segmentation masks that show like where the roads are on the satellite images. So I'll just show you that really. So here we have 4 different satellite images of Moscow. And then on the bottom, we have these purple images that show kind of the location of the roads, and they've been pre-labeled. But what all this information here talks about is how to create these masks, because all that the data comes with are these text files that kind of show you on a location by location where the roads are. So you have to convert that into an image for your neural network to understand where the roads actually are. So yeah, I won't go into too much detail about running this pre-processing script, but essentially what it does, it takes these text files, these GeoJSON road speeds, and it looks at the images themselves, and then it goes ahead and creates the speed limit mask images. And it also creates this CSV file, it's multiple CSV files for kind of binning the speed limits into, I think it's 8 bins. And so there are, like, if there's a speed limit that says it's 15 miles per hour, it'll round it up to 20. So it kind of goes in 10 mile per hour increments, like 10 miles per hour, 20 miles per hour, 30 miles per hour, et cetera. And so that's when you look at some of the colors on these speed limit maps, that's what some of those colors means, or some of the different speed limits that are associated to there. All right. So that's it for the training images and then the masks. And for training configuration, let me just look at the time. Okay. So there's a training configuration file, like a JSON file that you can fill out. Again, I won't go through all of these parameters, but it's something that you can read about on those Medium posts, and you can fill in yourself. But I've put the example of my config file, and then below this, I've also put, let me show you, I've kind of put like a description of the most important configurations that I kind of changed and worked through. But essentially, this is where you can set your pre-processing stuff, you can set your training stuff, you can set your inference. So things like your batch size, number of epochs, which loss function, and even you have a choice of models. You can try ResNet 50, you can try ResNet 101. So there's different networks you can try. So this is kind of the be-all configuration script that you would use, or JSON file that you would use for your training run. All right. So yeah, again, I won't go through all of these configuration parameters in detail, but they're here for you if you have questions about some of those different parameters. Okay. One of the first most training for most any machine learning training, you need to split the data into training and validation data. And so this genfold script will do that for you. And essentially you can say how much, in that configuration file, you can say how much training data you want. Like, do you want 80% of your images toward training and 20% toward validation? And then it'll split it into a CSV file, kind of saying which fold of your data are validation data and then which are training. So in my case, I have folds 0, 1, 2, 3, and 4. And the validation data are fold 0 for like 20% of my data. And then the training data are folds 1 through 4. And so here I'm showing like reading in one of these, the output fold scripts. And so all it really does is it shows this is the name of the image, and then this is what fold it's in. And then when you run your training, I'll show you this in a minute, you'll specify which fold you want to use for your validation data. So I can say, okay, I just want to use fold 0, and then all the, the images that are associated to that fold 0 will be used for validation, and the rest will be used for training. Okay, so now that we have kind of all that under our belt, there's some minor code-based changes that I needed to make. And these are what I'm hoping to kind of walk you through, in just a little more detail. And it's not actually that much. It's just, I would say, like 5 or 6 lines of code that we need to change in order to make this run, on the Intel CPU with AMX. So the first one that I'll walk through is making sure that the code runs natively on a CPU instead of a GPU. So sometimes people will put in like if CUDA and then else if it's on a CPU do this, but sometimes people just assume that it's always on a GPU. And so you have to kind of go into the code and remove some of those assumptions. So I'll go into the training script that you can find at this link from their GitHub, and kind of where I have to replace their code. So here they've put the model, they've defined the model, and then put this .CUDA, so kind of assigning it to the CUDA device. So all I have to do is just comment out that .CUDA. That's what I'm pointing out there. And then in the 0.1 train script, which is really what calls this train.py, when you run the training, you run the 0.1_train, and then it calls the train.py. And what they've done is they've inserted this torch random number CUDA, and it's basically just saying like, if you're on CUDA, great, it's going to run this command. If you're not, it's going to break, and it's kind of like a warning to you, like, oh, you're not running on a GPU, so you're going to have to modify a couple things. I think that's what their intent was there. So I'll just comment that out as well. Okay, so that's just making sure that the code runs natively on a CPU instead of a GPU. And before I get into optimizing the training code with Intel extension for PyTorch, for both training and inference, which is just 2 or 3 lines of code, what I want to do is I actually want to run training just with the regular PyTorch. And I've already, just so you know, I've already it, and I just want to get it started to show you, okay, this is what the approximate time is with when you just run like stock PyTorch. So I'll go ahead and do that. And so I'm going to skip down on the notebook to where I talk about beginning training. And the cool thing is that there are these helpers pointing out where we can utilize these to specify, we want this many instances of to run, so it just on one socket, and I want to run on 32 cores. Like I pointed out, there are 56 cores, but when you have kind of a smaller model architecture, it's not always essential to use your full core count, and it can even hurt you sometimes if you if you're trying to load everything all onto these cores, and then it doesn't even take you very much computation time, and you have to load everything off again. So sometimes it's helpful to go down in core count. You just kind of have to experiment with that. I didn't find a huge difference in modifying the core count. There was like very slight differences in training time. But the main difference that I saw was when I moved from training on 2 sockets to 1, because then it wasn't communicating across these 2 nodes. And so anyway, you can specify all those things with the stock PyTorch tool. There's something called Torch backend Xeon run CPU. And so you can actually run this, and you don't need to install, Intel extension for PyTorch or anything like that. And so the arguments are, like I pointed out, the number of cores, and then it asks you for a log path. And then here's my training script that I pointed out, the 01_train. And then I'm pointing it to my configuration file. And then at the very end, I'm saying fold equals 0, which means, just like I pointed out, that's for the validation data, just use fold 0. So I'm going to try to copy this. And there's always a risk whenever you do live demos. So it'd be interesting to see if it will run. But I'm going to go ahead and copy that in here, and then see if it will start running it, or see if I made any mistakes in my code. Okay, it looks like at least it pulled up the model architecture with all the different layers, and we'll see if it can get the epochs started for training. So it's I think it's probably about to be starting to load in the training data, and at least the script is running. Okay, now the epochs are starting, and it's showing that fold 0s is the validation data. That's just an output that it shows there. And then it's showing there's 135 iterations per epoch, kind of to get through all of the training data. And what you can see now is it actually gives you a time estimate of how long the training is going to take. And so the initial estimate was 37 minutes and 1 second. That's what that means. And then it also gives you how many seconds per iteration on the right here. And then there's some other things that talk about the loss functions. And then the total loss is really the most important one that you want to pay attention to, that it actually goes down with time, which we can already see it is going down. That's good. There's some convergence happening. And you can see that the estimate has already updated to around 29 minutes for the training here. And what I'll point out is that I'm not going to run, sit here and run the whole training. I just wanted to get it started to show you, the time estimate. But what I'll point out is that this first epoch takes around 30 minutes from what I ran. So I'm going to go ahead and cancel that now. Just Control-C, my favorite command in Linux. And most dangerous, maybe. No, maybe RN is more dangerous. Okay, so so I've canceled that training run. But what I would like to do now is try to optimize the code a little bit further with this bfloat 16. And so to do that, I'm going to do that both in the training code and then in the inference code. And it should only take me a few minutes here, because it's just a few lines of code to optimize it. So let's go ahead and do that. So the first one is we want to modify this train script again. And first thing we need to do is to add this IPEX import line. So I'll write import Intel extension for PyTorch as IPEX, just at the top of our imports. And just keep in mind too, I know that there's like simpler examples of like training. What I'm showing you here is I'm modifying this Cressy repository to include a few of these optimizations. So I kind of had to find, okay, when are they doing the things that I need to change a couple of lines? But it didn't take me too long. So then I'll find, so I've done that first bullet point on the left here. And then the next one is add a line for the IPEX optimization in bfloat 16 for mixed precision training, just after defining the model and the optimizer. So I know that some of this takes some familiarity with PyTorch. But yeah, once you're somewhat familiar with you model and then your optimizer. And so I have to add this line to kind of redefine the model and the optimizer. In this case, they're using the self variables in this init function. So I need to modify those and do ipex.optimize self.model, and then optimizer equals self.optimize or optimizer. Okay, and then here's key two, the data type equals torch.bfloat16. So that's saying, I want to use this bfloat16 data type, which should reduce our, our training time and computation. And then the next one is to add, just before we do a forward pass through the data and calculate our loss function, we want to add this automix precision line, this torch.cpu.amp.autocast. So I'm going to go ahead and look for that. I'll do calculate loss. Okay. So I'm going to add that here. So this output self.model input is where we're doing the forward pass through the data. So let's go ahead and add this line with torch.cpu.amp.autocast. And then we just want to use our tabs in Python to move that over. And that should be all I need for the training code. And then, so that's it for that should be it for the training code, fingers crossed. And then the next step is to optimize some of the inference code. And that's for at the very end when I show, running inference. And so it's very similar. In this case, it's just, let's just import ipex, and then we just do this ipex.optimize, and then again the CPU AMP autocast. So I'll run over to the eval script and go ahead and add this Intel extension for Python, or sorry, PyTorch. And I've already installed this with my pip install, so I know that I have this in the environment. Then I can look for torch.load. Okay, so okay, so in my case, I'm looking, they're going if torch CUDA is available. So that's saying let's look and see if there's a GPU, see if there's an NVIDIA GPU available. And then it's saying else. So, and that's my case, else because I'm running on a CPU, load the model. So basically right after this, it's right after you set the model to eval mode, which is, for inference. That's where we want to write out this optimize line and change the data type to torch.bfloat16. So that's, basically, okay. And then there's one more line to do mixed precision when we're actually running the prediction itself. So I'm going to look for data in pvar. I know I've already found all these things, with code, you sometimes have to look for that. Okay. Okay. And again, it's saying if torch CUDA is available. So I'm going to skip that because we're on a CPU. And then we're loading in the samples, the data. And then just before we run the prediction, we're going to do this with torch.nograd. And then with torch.cpu.amp.autocast. And then we should be able to just tab this over. And yeah, that should be all we need for the inference code. Okay, I'm going to try and save this. Okay, that's saved. Great. Okay, so now with the updated training code, I'll go ahead and run the training with this new ipex extensions. So again, I've pointed out kind of the script you can use, the helper script to run the training. And so the nice thing again is you don't have to explicitly set those Environment variables I pointed out with OpenMP and with NumaCTL. It does all that for you. And IPEX has something called IPEX run. And you can actually just run your Python training with this directly. And it comes installed with the Intel extension for PyTorch. Okay, so we'll copy this and we'll again hope for the best with a live demo with training and see what happens. See if I made any mistakes. Okay, so it's looking good. Again, it printed out the model architecture. It couldn't find like a previous model to train from, so it's going to start from scratch. Well, I say from scratch, but it's from a pre-trained network. I should probably point that out actually. So the model, and similar to most models, it's we're working from an ImageNet pre-trained model, and we're doing fine tuning. So that's the name of the talk. It's not training from scratch. So we do have pre-trained weights that we're using. Okay, so we can already see that the training has started. And in this case, our first estimate was 22 minutes and 56 seconds. Now that we're using kind of a more optimized framework, and we have this BF16, that's actually the main difference here as to why it's sped up, is using this BF16. And that's mainly what I showed you just now with modifying the code, was just adding these few lines to do the auto mix precision training. And yeah, so I'll point out again, I'll stop this in a second, but I'll point out that this training run in the first epoch takes around 15 minutes. I know that the estimate keeps updating, but it ends up taking around 15 minutes. So it's about 2 times as fast, which is great. So I'll go ahead and cancel that because I've already trained a model. And okay, so at this point, you would be done with the training. I'm kind of running a little bit long. I'll try to get. I'm pretty close to the end here. Tried to keep it to 45 minutes, but it might be 50 or so minutes. So during the training run, you can run this TensorBoard, which some of you may be familiar with, or maybe you use something like WANDB, where you can track the progress of your loss functions. So I've just given you some instructions there, but this is all kind of standard stuff. And then you can show this TensorBoard where you can show kind of your training loss and your validation loss as it's happening during training. It kind of just looks at a log file and extracts the information from there. Okay, and then inference. I'm not going to actually run inference right now, just for the sake of time, but I've pointed out, this is the eval, inference script you can run, and we've already modified the inference code to add the BF16. And then here, what I'm doing is I'm showing, okay, now that I have this trained model, I can predict on a satellite image, and then it'll output these masks. And it actually outputs them in 7 different bins, and then an aggregate. So an 8th bin is like an aggregate of all of the mask predictions from each of the channels. Because remember, there are, in my case, I trained with 8 different channels. I know I showed the RGB, the 3-channel, but I actually trained on the 8 channel, and it kind of puts these mask channel bins. And then finally, I'm showing, here's the satellite image that corresponds to that particular prediction mask. So you can see, it's output some of the roads that kind of go along with this satellite image. All right, so my internet just said I have internet unstable. Can you guys still hear me?
Yes.
Okay, great. So model limitations, I realized that the model that I've trained is overfit on the Moscow image data, and it likely would not generalize well to other cities. But the winning solution used data from 6 cities, and that's what I would recommend if you want to reproduce their results. So in the future, it would be really helpful to test training on all 6 cities and then running inference on another city to reproduce their results. So I'm aware that, I've kind of overfit this example, but the purpose was mainly to kind of showcase some of these cool CPU tools and the new hardware that I'm excited about. so, and then there are some post-processing steps. Again, I'm not going to go through those in detail. There's that Medium blog that kind of walks you through that, but it actually takes, the output of this mask and then converts it to a graph format so that you can actually put it on like a map, and you can actually use it for, speed limits and like distance for times to go between places. Yeah, so to recap today, summary of our accomplishments, we were able to create these training image masks with speed limits to correspond to our training satellite image data. We defined our configuration file for training and inference. We split up our training and validation data. We then optimized our code for CPU training, and then we went even further and optimized with this data format BF16. We trained a performant ResNet and UNet model, and then we ran initial inference to see the prediction on a speed limit mask. And then if you want to find much more detailed benchmarks, I have provided a link, including statements concerning the NVIDIA A100 GPU. But one thing I'll just point out is, I know, like, for me as a data scientist, I care more about the fact that I can do one of these training runs in like a day, like 8 hours or overnight, than about specific performance benchmarks. And so, but one of the things that this Sapphire Rapid CPU brings home to me, which is, it is newer to me, is that I can do fine training on a CPU, and that's exciting for me. It's realistic for me to do this, and yeah, so happy coding. And I do have a few calls to action. I'd be happy to, follow up with you. So the first one is if you could complete a survey. So I've posted that in the Zoom chat, and then if you want to start by using the Intel extension for PyTorch, you can just do a pip install, and try that out on your CPU. I think I should qualify it with saying, I think that it's maybe just for Linux and Windows. I'm not sure that the Intel extension for PyTorch works on Mac yet. I think that's a work in progress. And then number 3, get on the Intel Developer Cloud and get in touch with me if you want early access to, one of these machines. And then I'd be happy if you use the code, and you can connect with me on Discord. So I've provided that link as well in the Zoom chat, and I've put my username here, Silvos, hashtag 5002. And yeah, and then I'm in other places as well. So I'm happy to take some questions, and thanks for listening to me rant on for 50 minutes.
Yeah, thank you, Ben.
Yeah.
First, any question from the audience?
I don't have a question per se, but more of a statement. I'll say first, thank you for your time. It's great hearing the presentation and seeing the walkthrough. The thing that I like about the code that I saw is that it actually shows in the output how long it takes. I remember a professor I had at a workshop, it must have been about 5 years ago now, was telling me about an algorithm, some machine learning he was doing for a project, and it took him 2 days. So he decided to leave his computer on and walk away for 2 days and come back to it, not knowing how long it would take. So I'm glad that's been addressed, this code and with the software.
Yeah, no, I find that extremely helpful as well. And the fact that it actually gives you an estimate of, this is how long one little iteration of throwing a batch into your, your network takes. And then based on that, how long it thinks it's going to take for one epoch. And then if you're running for, say, 30 epochs, you would multiply that 15 minutes by 30, to get like an estimate of how long the whole training run will run for. So, yeah.
So I have a question. So you have shown the a performance improved, like faster, like a double speed for the training part. For the inference part, do you also observe like the similar, like that? Does it like also reduce the inference time?
No, you're right in saying that, like, I showed for training, and for this particular talk, I didn't spend a lot of time on the inference component, but there definitely is a speed up there. I don't have the exact number there for how much the speed up is or something, but I do want to do like a separate talk that's more focused on inference. One of the reasons that I was particularly like excited about showing training is because inference has been done on CPUs for a while. And even Intel has done a pretty good job with their CPUs on inference. But it seems like this time, like I'm really excited about seeing training being a possibility on the CPU. Just in the past, I've tried training on CPUs, like when I worked at my previous companies, but I ended up just switching to a GPU because it was too slow. But in this case, I was pleasantly surprised to see, oh, like this is actually a possibility to run training on a CPU, and it's pretty reasonable in time. And now I would say like it wouldn't be as fast as like the fastest GPU that's out there, but it doesn't really need to be for most fine tuning examples. Yeah, so it's kind of a answer non-answer, I guess. But yeah, I didn't spend a lot of time on inference this go around, but I do plan on doing that in a separate talk to kind of really measure the inference speed, because in production, what are we running? We're running inference, right? So that's what in production what we care about a lot more.
Yeah, because I do see like in production, sometimes there's like a latency limit, right? So the model, you cannot exceed, for example, like a 100 or 150 microseconds. And in order to reach that, well, the model cannot get that large. So, but if this like on the hardware side can help further reduce the inference time, that will enable kind of a larger model in production, I think.
Yeah, definitely. And CPUs in general, they do a pretty good job at low latency when you're doing like single batch or like really small batch inference, which some applications you have to do just very fast, like single batch inference.
Yeah.
So CPUs in general do a pretty good job with that. But yeah, when you're able to reduce the data type either down to BF16 or into 8, and quantize your model down, it can really accelerate like how quickly you can churn through data. And I have seen that. Yeah.